Hello again, this is Professor Roman. Let's continue the lecture's transition to advanced mathematics. In this lecture, we're going to talk about order. This is a very important topic in mathematics. It's essential to most branches, if not all branches of mathematics. So we're going to go over the basic notions related to the theory of order. The place to start is with the definition. Let P be a non-empty set. A partial order on P is a reflexive, antisymmetric, and transitive binary relation. And I'm going to denote a general partial order by this familiar less than or equal to symbol. It's not uncommon for symbols to get borrowed or generalized, and so we're going to have to talk about this a little more in a few minutes. Just because we are using this symbol does not mean that the set P has to be a set of numbers. It can be a set of any mathematical object, matrices, functions, polynomials, whatever, upon which there is a partial order, and that partial order can be denoted this way. Now, there are specific cases where there's a specific symbol, and then you would not use the generic symbol, and we'll talk about that again. This expression is read A is less than or equal to B. Again, we're borrowing from the prototype, which would be the real numbers with the usual order, less than or equal to. But we are generalizing here to arbitrary sets that have a partial order on them. We still use this terminology, A is less than or equal to B, or B is greater than or equal to A. We use this terminology unless there's a more specific terminology. This pair is called a partially ordered set, or poset, and P is the underlying set for the poset. If A is less than or equal to B, but A and B are not equal, then we would write this, again borrowing this symbol from the case of the usual strict order on real numbers. We would still read this as A less than B, or A strictly less than B. It would be better. It's common to hear a phrase such as let P be a poset, and that's unfortunate because the partial order is not mentioned, and that's dangerous because some common sets, like the natural numbers, have more than one important order on them. So it's much better to be more specific. It's better to write our posets as ordered pairs, where P is the set and this is the symbol for the order that you have in mind. And we'll see plenty of examples of this to make it clear, so don't worry about it right now. Another possible terminology is let P be a partially ordered set under, and then you mention the order. And I'll use that terminology as well. In a poset, we can define the notion of comparability of elements. So we have a poset, two elements A and B are comparable if either A is less than or equal to B or B is less than or equal to A. Otherwise, they are said to be incomparable or parallel, and the parallel symbol is used in this context. A poset, or partially ordered set, is called a totally ordered set, or linearly ordered set, if every pair of elements is comparable. So for every A and B and P, either A is less than or equal to B, or B is less than or equal to A. And then the order is referred to as being total or linear. this is critically important. We're going to see examples. And in fact, I think most of the ordered sets in mathematics are not totally ordered. They're partially ordered, which means there are elements that are not comparable. And I'm going to give you 2 or 3 really important examples of ordered sets that are partially ordered but not totally ordered. This is the more common situation. In real life, people tend to try to linearly order everything. This is the better chocolate than that. This is the better automobile than that. This is a better president than that. But sometimes, even in real life, things are not that simple. Okay? President X and President Y may be incomparable because President X has some skills that President Y doesn't have, and vice versa. So you can't say one is better than the other. You say they are, in technical terms, you'd say they're incomparable. Okay. If you have a poset, and if S is a non-empty subset of the underlying set P, then this is also, then S with the same order relation, but restricted to the elements of S, is also a poset. We say that S inherits the partial order from P. It's the same order, you're just restricting it to the elements of S, and that makes S a partial order. Some examples. The usual order on the set of real numbers is a partial order, and so this pair, where now this symbol does stand for the usual order because I said it did. This is, in fact, a totally ordered set. And so by what we just spoke about, any subset, non-empty subset, didn't spell that right, of R inherits the usual order and so becomes a totally ordered set as well. So the integers, the rational numbers, positive integers, they're all totally ordered sets under the usual order. Here are some important examples of partially ordered sets that are not totally ordered. The power set of a set S. This is ordered by set inclusion because set inclusion is reflexive, antisymmetric, and transitive. Here are the properties. That's easy to check. But if the size of S is at least 2, so S has at least 2 elements, say A and B, distinct elements, then the singleton subsets are not comparable because neither one is contained in the other. So as long as S has size at least 2, the power set of S is partially ordered under set inclusion, but not totally ordered under set inclusion. Another important partial order that's not total order is divisibility on the set of natural numbers. And we know what divisibility is, but just to repeat, we say that A divides B if there's an integer k for which B equals Ka. So B is an integral multiple of A. And this is the symbol, a vertical bar. And I should mention too, because I hear this from students a lot, it's a mistake, this relation is called divisibility, not division. This is a relation. We ask, is one natural number divisible by another? That's divisibility. Division is an operation. You physically divide one natural number by another. you get a quotient and a remainder. That's not what we're talking about. So do not use the term division in this context. The relation is called divisibility. Divisibility is reflexive, antisymmetric, and transitive, which I'll leave for you to check. And so it's a partial order on the natural numbers. But 2 does not divide 3, and 3 does not divide 2, so 2 and 3 are incomparable. And so this is not totally ordered. Okay, now we have two partial orders on the natural numbers, two common ones. The usual order, which is total, and divisibility, which is partial but not total. So this is a clear example of a case where a set can have more than one important order on it. Here's another order that is partial but not total that's also important. Let x and y be non-empty sets. So let's look over here. A partial function from x to y is a function whose domain is a subset of x. Codomain is y. Normally, when you say, and you're used to this in calculus, let f be a function from x to y. X is the domain, y is the codomain. That's why we add the adjective partial. A partial function from x to y is a function whose domain is a subset of x. It could be all of x, but it doesn't have to be. Codomain is still y. Now if you look over here, if we have two partial functions, then we say that the function g is an extension of the function f, and f is a restriction of g if two things happen. The domain of f must be contained in the domain of g. And on the elements in the domain of f, the two functions give the same value. Obviously, they can't outside the domain of f because f isn't even defined. So this is what the symbols look like. Domain of f is contained in the domain of g, and f of x equals g of x for all x in the smaller domain, domain of f. So as a quick illustration, the function f of x equals 1 over x is defined on the non-zero real numbers to the real numbers. This function g is defined on all real numbers, and it's defined this way. So if x is non-zero, in other words, if x belongs to the domain of f, it's also 1 over x. So g and f agree on the non-zero real numbers, but g has another value on 0, and it could have been anything, frankly. I just set it equal to 0. G is then an extension of f. Domain of f is contained in the domain of g, and on the smaller domain, the two functions agree. F is a restriction of g. G is an extension of f. And the set of all partial functions from x to y can be ordered by extension. F is less than or equal to g if g is an extension of f. So this is the generic symbol. I'm not sure whether there are common symbols for extension. I've seen a few symbols, but they don't seem to be consistent. So this is the generic symbol, but we're using it here for this specific order. And f is a restriction of g. Okay. That makes this set of partial functions into a poset. but generally not totally ordered. Only in extreme cases might it be totally ordered. Let me try to make it very clear about the terminology here. It's going to take a little time to get used to it. When you borrow specific terminology in general and apply it to more general situations, it can be a little bit confusing at first. The use of the phrase less than or equal to and this symbol is appropriate in really only two situations. Of course, it's appropriate when the underlying set is a set of real numbers, and and the order is the usual order. That's where these notations came from, and this language, less than or equal to. So it's still appropriate in those situations. The only other time it's appropriate is when you are talking about a generic or unspecified poset. Let this be a poset, and then blah, blah, blah. But you didn't say what P is. You didn't say anything about the order. It's got to be reflexive, antisymmetric, and transitive. That's all you know. A lot of theorems are phrased, let this be a poset. Okay? So that symbol is, in that context, this symbol is generic. It's not meant to indicate the usual order. And P does not have to be a subset of R. When there are commonly accepted symbols and language for a particular situation, you should always use that. So in this case, for example, the natural numbers under divisibility, you will use the vertical bar. If you use this symbol, you're asking for trouble, because virtually everybody will assume that you mean the usual order on the natural numbers, because that is the symbol for the usual order on the natural numbers. So you've got to use the specific symbol for divisibility. And you don't want to say, you do want to say 2 divides 4 rather than 2 is less than or equal to 4, because again, that's going to be misinterpreted as the usual order. As we have seen, this poset, the natural numbers under divisibility, is not totally ordered. It's a partial order that's not totally ordered. But this subset, for example, this is the set of all non-negative powers of 2, 1, 2, 4, 8, and so on, is totally ordered by divisibility. It's a subset of the natural numbers that is totally ordered by the order that's been inherited from the natural numbers, in this case divisibility. Totally ordered subsets of a partially ordered set play a very important role in the theory of partial orders. So we have a definition. Start with a poset, a non-empty subset, C, of the underlying set P, that is totally ordered by the order on P, is called a chain in P. Finite chains, not all chains are finite, and we'll see examples of an infinite chain, but finite chains therefore can be ordered. Since this is a finite set and it is totally ordered, we can find the smallest element, put that here, then the next smallest, and so on. You should probably go through this argument in detail, write down a formal proof of the fact that a finite chain can be written in this form. The length of a finite chain, in this case there are n elements in the chain. You might think the length should be n, but in fact it is defined to be n minus 1. It's 1 less than the number of elements. It is equal to the number of less than or equal to signs. if you think of those as the links in the chain, I guess you could say it's equal to the number of links. But in any case, that's the definition. So we have to live with it. If you have two elements A and B in your post set, A less than or equal to B, then a chain from A to B is a chain whose smallest element is A and whose largest element is B. So in this case, for example, C1 would be A, Cn would be B. Or we can simply say this is a chain from C1 to Cn. Another important subset of a partially ordered set is the exact opposite of a chain. In a chain, every pair of elements are comparable. In an anti-chain, no two elements, distinct elements, are comparable. An element is always comparable to itself. There's nothing we can do about that. That's reflexivity. But an anti-chain is a non-empty subset of a post set. I change that symbol. In which every pair of distinct elements are incomparable. I'll give you some examples that help clarify. In this post set, this is a power set, post set, under set inclusion. Here is the underlying, well, this is the set S. The underlying set is the power set of S. The family that consists of these three subsets of S, or in other words, elements of the power set, elements of our post set, is a chain. And you can write it this way, and that shows clearly that given any two of these three, one is contained in the other. Therefore, every pair of elements in this set are comparable. This family, however, fails to be a chain because if you look at these two elements, these subsets of size 3, neither one is contained in the other, so they are incomparable. So this is not a chain. This family, these four sets, four elements of the power set, is an anti-chain because if you take any two of these, they're not comparable. And you have to run through that by looking at all the pairs of elements, but it's pretty clear, I think, from this in this simple case. For this post set, the natural numbers under divisibility, this set is a chain, and here is the ordering, the total ordering for this chain. It is a chain of length 4, not 5. It's very tempting to say this is a chain of length 5, but that's not correct. By definition, it's one less than the number of elements. If you think about it, if you just had A less than B, that's a very short chain. How long should that chain be? I think 1 is not unreasonable for the length of that chain, so that's perhaps why the definition is the way it is. Here is an infinite chain, the set of all powers of 2. Okay. Obviously, since these are natural numbers, it's the non-negative powers. Okay. And the reason this is a chain is because 2 to the I will divide 2 to the j if and only if I is less than or equal to j. So given any two powers of 2, one divides the other. So that's an infinite chain. So you cannot do something like this for an infinite chain. The set of prime numbers in this poset is an infinite anti-chain, since no two prime numbers, distinct prime numbers, divide each other. Neither one divides the other, so they're incomparable. And we've already seen, in fact, we proved that there are infinitely many prime numbers, so that's an infinite anti-chain. In a totally ordered set, all non-entry subsets are chains. The whole thing is a chain, really. And so there are no anti-chains of size greater than 1. A singleton set is both a chain and an anti-chain. It's kind of by default. There's only one element, so all the elements in the chain are comparable. All the distinct elements in the chain are incomparable. Okay. On a matter of notation, it's very convenient to extend the use of the partial order symbol to subsets of a poset. So if S and T are subsets of a poset, then we're going to write S less than or equal to T to mean that every element of S is less than or equal to every element of T. Okay. It's a great savings in time to be able to write this rather than have to spell it all out. For all little s in capital S and all little t in capital T, little s is less than or equal to little t. You could say that, but this is so much simpler. Okay. And we also use this notation, which was really in place of this notation. So what this means is that every element of capital S is less than or equal to little t. And we'd have a similar notation here. Little t less than or equal to capital S means little t is less than or equal to every element in capital S. Example, in the poset of the natural numbers under divisibility, we could write this. And this simply means that every element in this set divides 20. It's a very convenient notation. And this is another example, meaning every element in this set divides every element in this set. Okay. Sometimes we can describe a finite poset using a diagram called a Hasa diagram. It shows the elements of the poset and it describes the order relation. And this is how it works. As an example, let's say we have this set of natural numbers under divisibility. That's a poset. This is what the Hasa diagram would look like for this poset. There's a vertex for each element in the underlying set, and this diagram is constructed so that if the elements x and y in the poset, and this would apply in general, in this poset, are connected by a path from x to y, and this is key, that goes up at every step. It must go up. Then x is less than or equal to y, and conversely. So you can read, in this case, 6 divides 72. Less than or equal to in this setting is divisibility. So 6 divides 72. 2 divides 72 because there's a path going up from 2 to 72. From 1 there's a path going to all elements because 1 divides everything. 2 does not divide 9. There's no way to get from 2 to 9 going up. You can go to 6 and then down to 3 and up to 9, but that's not relevant. You must always go up. Another way to think of this is to draw arrows always pointing up. Now you have a directed graph, something we've talked about before. I won't finish that. And then you can say that x is less than or equal to y if and only if there's a directed path from x to y. So this here would also go up. So you can't go from 2 to 9 in a directed path because you go this direction, but then you reverse direction here. I don't know that anybody draws the arrows. You can rely on the levels here in this to tell you which is up and which is down. Okay. So if you have to draw a Hasa diagram, it might take a couple of tries. You might place dots and label them and realize you have to tweak that a little bit. Some Hasa diagrams can get very involved. If we have a post set, and this is then a generic post set, so P is some non-empty set, and this symbol represents a generic partial order. In other words, it's all we know is it's reflexive, anti-symmetric, and transitive. We can define another binary relation, related binary relation, denoted by the less than symbol as follows. A less than B if and only if A less than or equal to B and A not equal to B. This you already know in the context of the usual order. You have the less than or equal to on the real numbers, and you have the strictly less than on the real numbers. And you get the strictly less than by ignoring the equality part, which is kind of what we're saying here. Okay. So in general, this works, and this relation is called a strict partial order. So there's a difference between a partial order and a strict partial order. I don't think anybody uses the term non-strict partial order, but it would be appropriate, I suppose, for this. I'm going to leave it for you to show that this strict partial order associated with the original partial order is asymmetric and transitive. Okay. So this calls for a definition. In general, any binary relation on a set A, and it's denoted with the strict less than symbol, is called a strict partial order if it is asymmetric and transitive. Now we saw in an earlier chapter on binary relations that asymmetry and transitivity is equivalent to irreflexivity and transitivity. So either some authors, if you look in different books, you will see the definition of strict partial order as asymmetric and transitive. In other books, you'll see it as irreflexive and transitive. So I figured I'd give you both. So if we have a partial order, we can produce a strict partial order, as we did up here. Conversely, if we start with a strict order relation, so that means we're presented with an asymmetric transitive binary relation denoted with this. Then we can define a non-strict, if you want, partial order by putting back equality. So A is less than or equal to B if and only if A is less than a B or A is equal to B. And this is a partial order, so you have to check that it's reflexive, antisymmetric, and transitive. But the fact is that we've already looked at this. This is the definition of the reflexive closure of the original order. I don't think there's a name for going in the other direction, for going from a partial order to a strict partial order. I don't think there's a name for that, but there is a name in going from the strict order to the ordinary partial order. It's called the reflexive closure. So we can go back and forth between partial orders and strict partial orders whenever we need to. They're strongly related because each one uniquely determines the other one. Nobody thinks twice about that for, say, for the real numbers with the usual order. If you automatically write down 1 is strictly less than 2 without even thinking about it. But you are, in fact, passing from a partial order to a strict partial order. The notion of bounds, upper bounds and lower bounds, in an ordered set occurs quite frequently in mathematics. You may have experienced some of that if you took calculus classes. And here's a case for this definition where we can get some advantage out of that extension of the order relation to subsets. It makes writing this definition simpler. We have a partially ordered set, and let S be a subset of P. An upper bound for S is an element in the poset, call it U, for which S, the whole subset, is less than or equal to U, meaning again that every element of S is less than or equal to U. Or perhaps it's better to say U is bigger than or equal to every element of S. That's what we mean by upper bound. And I'm going to denote the set of upper bounds for S by S superscript up, UP. I don't think this is standard notation. I'm not sure there is a standard notation. But this is certainly pretty clear what this means. Similarly, a lower bound for the set S is an element L in P, for which L is less than or equal to every element in the set, and we'll denote the lower bounds by S superscript low. A key point here, I've seen students make this mistake, or maybe that's too strong a phrase, to ask this question repeatedly. Does an upper bound for S have to be in S? And the answer is no. And this is a situation where there's a lesson here. If you're going to be successful at doing mathematics, you have to learn to answer your own questions whenever you can. If you look at the definition carefully, if you read the definition as a mathematician would, you will see that nowhere in this definition does it say that U must belong to S. It says U is a member of the poset. It has to be, obviously. But there's nothing here that says U has to belong to S. Therefore, if the definition is correct, if I didn't make a mistake, and I certainly make lots of them, in this case I didn't, you shouldn't read something into a mathematical statement that's not there. So you could answer that question for yourself. Okay. Example, in the power set poset under set inclusion, this is the set X. This family, 3 elements of the power set, will have many upper bounds. An upper bound is a subset of X that contains these 3. because containment is the order in this case. The smallest upper bound is then the union of these three, because by definition, that's the smallest set that contains all three of these. And the union is the set 1, 2, 3. In fact, any subset of X, any element of the power set that contains the union will be an upper bound for this family. The most efficient upper bound, the smallest one, is the union itself. Another example, two natural numbers in this poset, the natural numbers under divisibility, then an element X is an upper bound for this doubleton set if and only if it is a multiple of both A and B. In other words, a common multiple of A and B. And so, again, there's a least upper bound in the sense of divisibility, and that's going to be the least upper bound of A and B. X is a lower bound if and only if it's a common divisor. There'll be a greatest lower bound, and that is the greatest common divisor. We're going to actually come back to those issues of least upper bound and greatest lower bound. Right now, I'm just interested in explaining upper and lower bounds in general. In some posets, two distinct elements can be as close as possible without being the same, so they're distinct. Here's the formal concept. We have a poset, two elements A and B in the underlying set. We say that B covers A, and this is the notation I'm going to use. I'll talk about notation in a minute. And you would read this as B covers A, or A is covered by B. If two things hold, first of all, A is less than B, so they are then distinct, and there are no elements strictly in between A and B. So this can never happen. There's no C in the poset that is strictly between A and B. Another way to say that is if C is in between A and B, C has to either be A or it has to be B. So these are equivalent statements. There's no C for which this holds and is equivalent to this statement. Okay. Unfortunately, there's a lot of different notations to denote covering. This is common, and it's the one I like, so I'm using it. This one is possible, but it's a little tricky to write this curly stuff by hand. Sometimes it comes out straight. It looks like a strictly less than symbol. This one's a little bizarre. I don't like these two symbols together like that. It looks awkward. This one's cute, but I don't use it. I don't care for it. So we're going to use this first notation. Example. Again, we have the power set, poset under set inclusion, two subsets of S, in other words, two elements of the power set. Then B covers A if and only if B is a proper superset. So it is strictly larger. It contains A, but something else as well. In fact, B has exactly one additional element that's not in A. So take A, toss in one more element that wasn't there. You'll get B. That'll be a cover for A. Any way you can do that. You can take A, throw in any element you want, assuming there are some other elements in the poset, and you'll get a cover. But if you throw in two elements, it's not a cover. It's an upper bound, but it's not a cover, because there's something in between. So this is the symbol. A is covered by B if and only if B is A union a singleton subset. So we're tossing in X. X is in the underlying set, but it's in S. I said this twice, and both times I was wrong. The underlying set is the power set. Okay. S is not the underlying set for the post set. It's the underlying set for the power set. So that's a little confusing. Anyway, X must come from S but not be in A. So we get a singleton subset. This is a cleaner way to do it if you're comfortable with this disjoint union. If you write something for someone outside this class and you use this symbol, intending it to mean disjoint union, unfortunately, you're going to have to say that, because you can't rely on other readers of your material outside this class to know what this symbol means. So I did it here, where this symbol is the symbol for the disjoint union. Notation can be a tricky thing. It's dangerous to assume that your reader knows the same notation you know. For obvious things, there are obvious symbols that everybody knows, but symbols like the disjoint union, maybe even divisibility, should at least once in your writing be explained. You can do that at the beginning. You can say, in the following, we're going to use this notation, and here's a list of your notation. You could, each time the first time a symbol comes up, you could explain it. The problem with that is, if you're writing something in multiple pages, and somebody is reading it over multiple days, they may forget what the symbol means, and then they'll have to struggle through your paper looking for the first occurrence of that symbol in the hopes that you've explained it to them. So it's better if you put it at the beginning or at the end. My books have an index of symbols that comes at the end of the book right before the main index. So anytime a reader sees a symbol and it's not been introduced earlier, or they've forgotten what it means, they can look in the index of symbols. That's a very important courtesy to the reader. If it's one page, if your document is one page long, you don't have to worry about that. But if it's much longer than that, then this is something you should take into account. Here's another example of covering or non-covering. The real numbers with the usual order. No element covers any other element, because if you have two real numbers, A less than B, there are plenty of, in fact, infinitely many real numbers strictly in between. One example, of course, is the average, A plus B over 2. So there's no such thing as two real numbers that are as close to each other as possible without being equal. It can't happen in the real numbers. Just a note, if you look back at the Hasa diagram, the covering relation is defined by the individual lines in the Hasa diagram. So let me page back here. Let me find that Hasa diagram. It was about 3. There we go. 4 covers 2, and 27 covers 9, 72 covers 6. Single line indicates a covering relationship.